So let S2 square over S1 square equals W. Okay, then write our lambda as n1, n2 to the n1 plus n2 over 2, and we have W n2 over 2, and we have n1 plus n2 W to the minus n1 plus n2 over 2. Okay, so less than lambda 0. So we write everything in terms of W right now. So let's take the ln of both all sides, or let's write the okay, so let's take the ln of both sides and write the constant on to the other side. So we will have n2 over 2 ln w minus n1 plus n2 over 2 ln n1 plus n2 w less than ln lambda 0 minus minus the constant part. Okay, so this part not that important. So let's say this is our k, and let's say this is our z. Again, we have a function. So what is our aim? Our aim is to write this z function as a just function of w and try to find the rejection region in terms of w's only. So again, let's try to search for the shape of the distribution of z, or the form of the z. So what we are doing, first of all, we want to see does this function any peak point, minimum, maximum values. So then we can draw the shape of the approximate shape of this function, and then we can with respect to w, and then we can see we can write the rejection region in terms of w. So when we take the derivative of z with respect to w, so we will see n2 over 2w here, and we have minus, not plus, we have a minus sign, n1 plus n2 over 2, 1 over n1 plus n2 w. So we have n2 here, equated to 0, and when we solve it, this w, we will end up with w equals to 1. Okay, so to see this point is a maximum point or minimum point, so let's take the derivative again. So we will have minus n2 2w squared. Now we have plus, now n2 squared divide by n1 plus n2 w whole square, where w equals to 1, this quantity is negative. Okay, so this means that this w is the maximum point of z. Okay, so let's draw the shape of the function z. So here, let's see, go back to the function w. So when we replace w by 1, so this part will be 0. So this part will be minus these quantities, and we will have ln n1. n1 is positive and greater than 1, so it's positive. So we have a negative z value under the peak. Okay, so let's draw w versus z. Okay, so then we have something here, and this is the peak point where lambda is 1. Okay, and so let's say this is our k. So this is our rejection region in terms of z. Okay, so we will reject our null hypothesis when z is less than k. So this is the rejection region with respect to z. With respect to w, what we have, okay, so the values less than this k1 value, and the values where w greater than k2 value will be our rejection region. Okay, so now we can write our rejection region with respect to w's. Okay, so then we can write reject H0 if W, which is S2 square over S1 square less than K1, or the same W, which is this one, greater than K2. Okay, so now this our rejection region can be written as a function of one test statistic. So it's nice. So now we have to find K1 and K2. So again, these parts are the same. So again, using the type of error probability, we can easily define our test statistic. So but before that, going to that, so let's try to find the distribution of W, or how we can ended up. So we started with normal, remember, and we are ended up with the ratio of two population variances. So as you can guess, we will ended up with F distribution, right? So we have N1 S2 square over sigma 1 square. So this distributed as chi square with N1 minus N1 minus 1, and for the Y term we have this one, and we have chi square and 2 minus 1, and since x and y are independent, their functions are also independent, remember. So when we combine these, so we have so here in the statistic we have sigma 2 over sigma 1 square. So let's write the second term in the numerator, and 2 s2 square over sigma 1 square divided by its degrees of freedom. Okay, and do the same thing here. Oh, sorry, this should be sigma 2 square, sigma 1 square here, 1 over n minus 1. So this should distributed as f and 2 minus 1 and 1 minus 1, right? Okay, so let's write this in a nicer way. Then we have n1 minus 1 over n1, and we have n2 over n2 minus 1, s2 square over s1 square, and we have sigma 1 square divided by sigma 2 square, and this distributed as f with these degrees of freedoms. Okay, then when we consider our null hypothesis, or if we so let's see, that's the square in. Okay, so if we focus on the part where we have this n2 s2 square divided by n2 minus 1. So what is our s2 square? Let's write it. yi minus y bar whole square divided by n2, and we have n2 minus 1, right? This n2, these terms are cancelled out, and now we have an unbiased version of the sample variance for y. Okay, so n2 minus 1. So let's write this as n2 star square. Okay, and do the same thing here. So now our test statistic turns out to be a function of unbiased version of the sample variances. Okay, so n1 and 1 minus 1, and we will have xi minus x bar whole square divided by n minus 1. Let's name it as s1 star square. Okay, so now our f actually becomes sigma 1 square over sigma 2 square, and we have s2 star square, s1 star square, and we know that this is f distributed, and under h0, where sigma 1 square equals sigma 2 square, this quantity under this quantity will be 1, right? So if we name it as f0, so we have s2 star square divided by s1 star square only, and under h0 this has again the same distribution. Okay, so now everything is based on RW. As you can see, with the multiplication of some constants actually. So again, let's use the definition of type 1 error, which is the reject H0, where H0 is true case. Okay, so what is that probability that we have S2 squared? These are all capital random variables, K1. So sigma 1 square equals sigma 2 square, plus we have or S2 square over S1 square greater than K2, again under sigma 1 square equals sigma 2 square. Okay, so let's add the constants. So n1 minus 1 over n1, n2 minus 1. Okay, so S2 square, S1 square, and add the same constants here under the condition this, plus do the same thing to the other side. Actually, let's write this as S2 star square divided by S1 star square. Then this part will be S2 star square divided by S1 star square greater than this constant. K2 given sigma 1 square equals sigma 2 square. Under this hypothesis, remember, and let's make these K1 functions nicer. So this is not that important. So let's write this as C1 and this part is C2. Okay, then under the null hypothesis we have F0, which is distributed as F, less than C1, given sigma 1 square equals sigma 2 square, which is 1 actually when we get the ratio, and then write the same thing here, greater than C2, sigma 1 square, sigma 2 square equals 1. Writing the distribution of F0, so we have n2 minus 1 and 1 minus 1, here less than C1. We don't have to write the condition right now because we know the distribution under the null hypothesis now. Okay, so now for simplicity, take alpha over 2 for simplicity. Okay, then we have to use the F table, right? It is, the right skewed, n2 minus 1 and 1 minus 1. So we need to find these areas and the points. Alpha over 2. So this point is C1 and this point is C2. And in terms of F, this is what? This is n1, n2 minus 1 and 1 minus 1, alpha over 2. And this one is f of n2 minus 1 and 1 minus 1, 1 minus alpha over 2. Okay? Then we know our C1 and C2. So we can write likelihood ratio test of size alpha will be reject A0 if F0, which is S2 star square over S1 star square less than F n2 minus 1 and 1 minus 1, 1 minus alpha over 2, or F0, which is S1 S2 star square divided by S1 star square greater than f n2 minus 1 n1 minus 1 and alpha over 2. So this is our test. So you can write this test in terms of s1 over s2 square, and in that case all you have to do is change the order of the f, so you will end up with the same test. So this is how we derive the test. So let's find the power function. Pi for different ratio for sigma 1 square and sigma 2 square. So again, we have to consider the probability of reject A0 under whole parameters. Okay, then our test is what? We have f0, which is less than f this 1 minus alpha over 2, given all parameters. Okay, plus where our f0 is greater than n2 minus 1 n1 minus 1 and alpha over 2, given mu1 mu2 sigma 1 square sigma 2 square. Okay, so now what we have to do is write our true sigma values given in the power function. So we have sigma 1 square over sigma 2 square f0 less than sigma 1 square sigma 2 square f value given the parameters plus the same thing now greater than. So this is not the most powerful test actually, so the power of this test is lower compared to one-sided tests. But sometimes we need to do this, although we know that the power is low. So now this is distributed as f and this is distributed as f. So we have a probability that f, these are the degrees of freedoms now again, which is less than sigma 1 square over sigma 2 square f and table value plus f n2 minus 1 and 1 minus 1 are greater than n2 minus 1 and 1 minus 1 and alpha over 2. Okay, so this is the end of the power calculation. So as you can see, it's very long to solve, so you can try to solve the questions for let me give you an exercise where we have two exponential values, random sample of size n, let's say, and y exponential theta 2, same sample size, let's say, and these are independent from each other. And let you derive the case theta 1 equals theta 2 versus theta 1 not equal to theta 2. So find the generalized likelihood ratio test of size alpha. So this is an exercise for you. Okay, so in the next video we will see how to derive the sequential probability ratio test, SPRT, and we will see some examples related to that.